Guys, we'll be starting in a few minutes. We'll be starting at 10:35.
Hello everyone, welcome to the Mathematics Club Summer School 2023. Today we will be seeing few basics of probability and then we'll go into the further higher topics of probability today. So hope you will enjoy this session. So to start with, what is probability? What are the different interpretations of probability? And what are the areas of applications of probability? So anyone can respond in the chat. What is probability? What do you think probability is? Yeah, chances of an event to occur. Yes, yeah, that's nice. So we'll answer first. What is probability? Speaking generally, probability is nothing but a chance. So when you toss a coin, what is the probability of getting a head is same as what is the chance of getting a head. So the probability of an event of occurrence is nothing but the chance that the event will occur. More formally, probability of an event is the extent to which the event is likely to occur. Uh, so let's take a dice and we are going to throw it. So the possibility, the extent to which the number 1 can appear or 2 can appear is same as the probability of the number 1 appearing on the dice or something. So formally, probability is a number in 0 to 1. What are the different interpretations of probability? Theoretical interpretation, like that comes from the mathematical modeling or logical reasoning. So someone can answer, if we toss a coin, what is the probability of getting a head? Yeah, it's 0.5. How are we calculating? Like we are theoretically calculating that there are two possibilities, heads or tails. The possibility of getting head is 1 out of 2. So it is 0.5. So this is we are calculating it theoretically. So it is a kind of interpretation for probability. So it is theoretical interpretation of probability. And empirical or experimental interpretation of probability. So it comes from long run of observation. So basically, what is the difference between theoretical and empirical? Theoretical is something we determine theoretically. Like there are two choices, we can get one. So it is 1 upon 2. Empirical, like we don't look it by taking one trial or two trials. Like we'll perform the experiment for a long number of times. So it's like we'll toss the coin for 1,000 times or 10,000 times and we will see how many times head occurred. So the empirical or experimental probability is given by the number of occurrences of head upon total tosses. Or the third interpretation is subjective. So what is subjective? So sometimes we go outside and see if it is cloudy, then we'll say probably it might rain today. So what is that probability means? So it comes from our experience or intuition based on the previous knowledge. So it is subjective. It is subjective interpretation of probability. So you can see here different interpretations of probability. What are the areas of application of probability? Why do we need to study probability? Yes, we'll see. Sports strategies, modeling randomness. Like there are different applications, practical and theoretical as well. So you can see them here. So practical applications, there are sports strategies, insurance, politics, weather prediction, natural disaster prediction, traffic estimation, and so on. Theoretical applications, modeling randomness and measuring uncertainty, used in applications of artificial intelligence, used in statistics and various fields of mathematics, physics. So what are the basic terminologies in probability? Random experiment. It is the underlying process which produces exactly one of several outcomes. So for an example, let's take a dice. We are throwing it. So there are 6 possible outcomes and only one will occur at a time. So all, like more than one can't occur. Like if we throw a dice, we can get either 1 or 2 or 3 and so on 6, but not any two at the same time. So that kind of experiments are random experiments. Sample space, the set of all possible outcomes. So like while throwing a dice, what is the sample space? Someone can respond in the chat. What are the all possible outcomes? Yeah, fine. So the sample space of throwing a dice is 1, 2, 3, 4, 5, and 6. What is an event? A subset, any subset of sample space is called an event. So uh, for a dice throwing, the event can be either getting 1, 2, 3, or 4, or 5, or 6, or it can be a combination of few of them. Getting odd number. So getting 1, 3, 5, it is an event. Getting even number, getting 2, 4, 6, it is an event. Getting a prime number, it is an event. So any subset of sample space is called an event. So a event can be a null set, or it can even be the complete set, complete sample space as well. So we'll see examples. Let us take a coin. Then our experiment may be tossing it once, twice, thrice, or n number of times. Any of this may be our experiment. Let us say our experiment is tossing the coin twice. Then the sample space will be getting both heads, or first head, second tail, first tail, second head, or both the tails. So there are a lot of possibilities for our events. So any subset of the sample space is our can be our event. So you can see there are different events. Is that clear? Here the event HH means the outcome of both tosses is head, and HH comma TT means uh, the outcome may be both head, or the first toss is head and the second toss is tail. Why is phi a event? Okay, so if I am expecting nothing, like I should not get anything. In the two tosses, I should not get head or tail. So it is also event, but its probability is 0. Phi is the empty set. So moving on, visualization of steps, sequential steps. The probability of sequential steps can be visualized in the form of trees. In the previously mentioned sample space, can be visualized as a tree. So see, we are starting like we haven't tossed the coin. So if I toss a coin, the first outcome may be a head or a tail. So we indicate it in the first branches of a tree, head and tail. So if the first toss is a head, then for the second toss we have two possibilities, head or tail. So it further goes into two branches. If the first possible, if the first outcome is a tail, we have two more possibilities for the second outcome. It can be a head or tail. So we can visualize a process or an event in the form of sequential steps. This tree, the two nodes represent the possibility of first outcome, first row, and the next four represent the outcome of the second row. So you can try constructing sequential steps for throwing a dice or something. You can try it yourself. Choosing a sample space. Like, can we choose anything as our sample space? Are there any restrictions? So let's say you're tossing a coin. Uh, so can I choose my sample space as getting head, getting tail, and getting one or getting two? Is it a correct sample space? No. No. The answer is no. Why? Because the sample space need to have certain conditions, like it should satisfy certain criteria for being a sample space. So different elements of a sample space must be mutually exclusive so that when an experiment is carried, there is unique outcome. So when an experiment is carried, there should be a unique outcome. Like there should be no overlap of two elements in the sample space. The sample space must be collectively exhaustive. That is, whatever may be the outcome of the experiment, it should be in the sample space. So while tossing a coin, I can't just simply take getting head as my sample space because it don't include the possibility of getting tail. So when we take the all the elements of the sample space, then it should give the complete all possible outcomes of this event. We should be very careful and choose our sample space properly. Like we can't randomly choose whatever to be our sample space. We should choose it very carefully. Probability law. P of A is the probability of event A, then P of A must follow certain rules. We combine these rules into probability law. Non-negativity. For any event A, P of A must be greater than or equal to 0. It should be the probability of any event should be non-negative. It can be either 0 or it should be greater than 0. Additivity. If A and B are true disjoint sets, then their union satisfies P of A union B equals to P of A plus P of B. So disjoint sets means there are no common elements between A and B. In such cases, P of A union B is P of A plus P of B. This can be extended to any number of disjoint events. So you can take even three events which are disjoint A, B, C. So P of A union B union C should be same as P of A plus P of B plus P of C. Normalization. The probability of entire sample space omega is equal to 1. So if we take the entire sample space as our event, the probability should be equal to 1. So is that clear? Discrete probability models. So what do you mean by the term discrete? Discrete. It means stepwise, like it's not continuous, it's parts. See, the natural numbers are discrete, 1, 2, 3, and so on. Like there is no number between 1 and 2. So it's discrete. Discrete probability law. Yeah. If the sample space consists of a finite number of possible outcomes, then the probability law is specified by the probabilities of events that consist of a single element. In particular, the probability of any event S1, S2, and so on Sn is the sum of the probabilities of events P of S1, S2 is equal to sum of individual events. So, see, like if you are tossing a coin twice, so the sample space is HH, HT, TH, and TT. And our event can be getting both the outcomes to be same. So our event is HH, comma TT. So here we can take our S1 as HH and S2 as TT. So what is the probability of event? So P of HH comma TT is same as P of HH plus P of TT. This is discrete probability law. Like when it's not continuous and you can get differently, then you can add the probabilities. Discrete uniform probability law. If the sample space consists of n possible outcomes, which are equally likely, that is all single events have same probability, then the probability of any event J is given by P of A equal to number of elements of A by n. So what is it? So when you throw a dice, what is the probability of getting 1 or any number? One by 6. So it is same for all numbers 1, 2, 3, and so on 6. So if I ask you, what is the probability of getting either 1 or 2 or 3? So basically, what we are doing is we are counting how many elements are there in A. 1, 2, 3. There are 3 elements. So our event is 1, 2, 3. So number of elements in our event are 3. So the numerator is 3 and the denominator is n. Total number of elements in the sample space 6. So it's 3 by 6, which is 1 by 2, which is 0.5. Yeah, good. So some properties of probability laws. Consider a probability law and let A comma B comma C be 3 events. So if A is subset of B, then P of A must be less than or equal to P of B. If A and B are 2 events, necessarily need not be disjoint. So if P of A union B is equal to P of A plus P of B minus P of A intersection B. So the second point implies the third. So since probability is non-negative, we are subtracting something from P of A and P of B to get P of A union B. So P of A union B is less than or equal to P of A plus P of B. A union B union C is same as P of A plus P of A complement intersection B plus P of A complement intersection B complement intersection C. So what does this mean? P of A, the probability of getting A. And are we including all the things by taking only P of A? Are we including all the terms required for the probability of P of A union B union C with the term P of A? No, right? So we are missing out some terms which are not in A but are present in B or C. So we are taking A complement B. So which are not in A but are present in B. And then are we including entire things? No. There might be some things which are not in A and B but present in C. So P of A complement B complement A complement intersection B complement intersection C gives those possibilities. And P of A plus P of A complement equal to 1. So the probability of any event occurring plus the probability of that event not occurring is equal to 1, which is nothing but the entire sample space. So continuous probability models. Before we have seen discrete probability models, now we are going to see continuous probability models. Probabilistic models with continuous sample spaces differ from their discrete counterparts in that the probabilities of a single element event may not be sufficient to characterize the probability law. So what does this mean? So if I ask you to choose any real number, like if I ask you what is the probability of choosing 0.5 from the number line 0 to 1? Yeah, the probability of a single element event must be 0. Yes, it is 0. Because if it is something finite, then we have infinite number of such events. So the probability goes infinite. But we have a restriction that the probability can be maximum of 1. So the probability of single element must be 0. So, but how to observe such kind of probabilities? So if I ask you, like what is the probability of choosing a element between 0 and 0.5 from the number line between 0 and 1? What is the probability of that? 0.5. So what are we doing? We are taking the probability that 0 to 0.5, it is a length of 0.5 on the number line from 0 to 1. So we can choose that. So here is an example. A wheel of fortune is continuously calibrated from 0 to 1. So the possible outcomes of an experiment consisting of a single spin are the numbers in the interval 0 to 1. So the above problem, it makes sense to assign the probability b minus a to any subinterval a comma b of 0 comma 1. So if I ask you what is the probability of getting numbers between 0.3 and 0.7, what is the probability? Yes. And to calculate the probability of a more complicated set by evaluating its length. So since we are taking a single calibrated number line, it is length. If we have plotted something in terms of 2 dimensions, then it would be area. If we have taken some 3 events going on, then 3 things going on, then it would be a volume in 3D. So note as this scale of spin is 1 dimensional, we are using the term length, but in general, it is the length of n dimension. That is, area is length of 2 dimension, volume is length of 3 dimension, and so on. Is that clear till now? Like there is a fun problem. You can try it yourself. Srija and 2C decided to meet at ESB at some time between 11 a.m. and 12 p.m. And the one who comes first will wait for at most 10 minutes for the other persons to come. What is the probability that they will meet? you can try it later on and we can discuss in the group if any doubts are there. So you try this, like, see what are the possibilities, like how to represent it. You think in different possible directions, like how to represent it as a continuous probability model. Is it a line or is it a area or it's a volume? Just think about it and we'll discuss. So see, think about it, we'll discuss. Hint. So we'll give you a hint. Try putting the time of arrival on XY plane and see the sample space and favorable event. So I can see many people saying 1/6, but sorry, it's not 1/6. You can try another possibility. Later on, we'll discuss it in the group. Yes. Moving on, back to P and C. So few of the many probability models, like we have seen different things. So when it comes to discrete norm, like discrete uniform probability, what we have is total number of elements in the denominator and favorable cases in the numerator. So we need to count how many cases are there in different ways. So we need to include some P and C in this. When we have countable sample spaces, then we can use counting principles to calculate the required probability. In such situations, probability of a given is given by number of favorable cases by total number of cases. So let's see example. You toss a fair coin twice. The probability that you will get both heads. So see, our sample space contain only 4 possible outcomes. And our favorable case is only 1. So 1/4, which is 0.25. Is that clear till now? I- Are everyone with me? Is that clear? Yes. So we'll revise few basic counting laws. Addition rule. If an event can occur in m ways and a second event with no common outcomes can occur in n ways, then the first or second event can occur in m plus n ways. So what does this mean? Let's say you are inside a room and you have 2 doors on your right side and 3 doors on your left side. So you can leave the room from either of the 2 doors or these 3 doors on the left side. So what are the total number of ways you can leave the room? 5. So what are you doing here? You can go from either left side or right side. So you are adding both. Like you have 2 ways on right side and 3 ways on left side. So total number of ways is 5. Yes. Multiplication rule. If one event can occur in m ways and the second event can occur in n ways after the first event has occurred, then the two events can occur in mn ways. So let's say you are going from city A to city B and then to city C. So you have 3 routes from going from A to B and 4 routes from going from B to C. So in how many ways you can reach to C from A? Is the question clear? Like you have to go from city A to city C and you have to go through city B. Yeah, it's 12. So basically, let's say you have A, B, and C. You have three possible ways to from A to B and four possible ways from B to C. So in how many ways you can go from A to C? So you can go from A to B from either of these three ways and then from B to C in either of the four ways. So total number of ways will be 3 into 4, which is 12. Yes. Then some basic counting principles. A number of ways of arranging and distinct objects. So for this, let's take an example. Number of three-digit numbers formed using 1, 2, and 3. Hmm, like number of ways of arranging n distinct objects such that none of them is repeated. Like see how many three-digit numbers containing distinct digits you can form using 1, 2, and 3. Yeah, it's 3 factorial. Number of ways of arranging r distinct objects taken from n distinct objects such that none of them is repeated. You can do it in NPR ways. So now I am not going to put restriction on the digits. You can take anything from 1 to 9 and you can form 3-digit numbers. Number of ways you can do that. Yeah, it will be 9 into 8 into 7, which is 9p3. Yes. Number of ways of arranging n objects, of which r are identical and remaining are distinct. So, uh, if I ask you, how many different permutations are there for the word apple? APPLE. So it will be total. You have 5 words out of 5 letters, out of which 2 are repeated. So it will be 5 factorial by 2 factorial. So similarly, the number of ways of arranging sigma like n1 plus n2 and so on nk objects, of which n1 are of one kind, n2 are of other kind, and so on, will be n1 plus n2 plus and so on nk factorial by n1 factorial into n2 factorial and so on nk factorial. Yes. The number of ways of choosing r objects from n given objects is NCR. So you can see NCR, which is equal to n factorial by n minus r factorial into r factorial. So is this clear till now? Yeah. So now we will see example. Pass or fail. 2C is a give 2C is giving an exam consists of 3 questions randomly selected from a collection of 250 problems. To qualify the test, he needs to solve at least 2 of the 3 questions. If 2C knows how to solve half of the 250 questions, then what is the probability that 2C passes the test? I'll give you 2 minutes to try this out. You can try solving it. Like, how would you proceed? So I can see few answers: 125 C3 by 250 C3, 62.5. See, the probability is a number between 0 and 1. So you have to normalize it. Uh, I could see someone giving 125 C2 plus 125 C3 by 250 C3, 125 C1 plus 125 C2 into 2 by 250 C3. Yeah, I could see a correct answer. Yes, so you can see here. We'll see how to solve this problem with counting principles. So let us first calculate the number of elements in the sample space, uh, which is same as number of possible question papers consisting of 3 questions out of the 250 questions. So what is it? 250 C3. Like, out of 250 questions, I can choose randomly any 3 questions. So it is 250 C3. Now let us see the possibilities where 2C can pass. That is question papers in which he knows all 3 questions, or paper has 2 known questions and 1 unknown question, which is equal to 125 C3. So since he knows half of the questions, 250 by 2, 125. So among these 125, if he is lucky enough, he will get all 3 questions correct. So 125 C3. If not, he has to pass. So he have to get at least 2 questions from this 125. So which is 125 C2, and we have to choose 3 questions. So one question from should be from the other 125. So which is 125 C1. So the total number of possible question papers such that 2C can pass is 125 C3 plus 125 C2 into 125 C1. So the probability of 2C qualifying the test is the favorable cases upon total number of cases. So which is 1 by 2, which is 0.5. So is this clear? Is everyone with me? Is this clear? Yeah, good to go. So we'll have something interesting which is called birthday paradox. You are choosing n people randomly, then what is the probability that at least 2 of the chosen people have same birthday? Look, I'll give you 2 minutes so that you can try. I can see answers 1 by 365, 365 by 365 C2. So more answers, like you can try. Okay. So give me like what is the sample space? Like in how many different ways these n people can have their birthdays? What is the sample space? assuming it's not a leap year. What is the sample space? $365 per n. Yeah. So this kind of problems will solve by using complementary. Like we have seen, P of A plus P of A complement is equal to 1. So if you want to calculate P of A, we can calculate P of A complement and then we can subtract. So we define A, the event that at least two people have same birthday, which implies A complement, that no two people will have the same birthday, which implies P of A equal to P1 minus P of A complement. The total number of possible ways that their birthdays can be. So each of the n person have 365 days. So any of the day can be his birthday. So 365 for the first person, 365 for the second person, and so on, n person. So 365 power n is our sample space. So for A complement, we should have that no two people should have same birthday. So we have to choose n dates from the 365 dates, and we have to arrange them for these n people so that no people have same birthday. So in how many ways you can do that? 365 pn, like you have 365 days, you have to take n of them and arrange them for these n people. So number of ways you can do is 365 pn. So what is p of A complement? 365 pn by 365 power n. That is, no two people have same birthday, which implies p of A is 1 minus p of A complement, which is 1 minus 365 pn by 365 power n. Then the probability that at least two people have a common birthday is 1 minus 365 pn by 365 p whole power n. The interesting thing is, if you are choosing n random people, like how many people do you think are required such that the probability that any two persons have same birthday is greater than half? Yeah, it's 23. Something interesting. You randomly take n equal to 23 people, the probability is more than 50%, which is amazing, right? Like we don't expect something like a small number like 23 to give us such a huge probability, which is greater than half. So uh, basically, like when you are thinking in terms of numbers, like what would you think? To have at least two people with a common birthday with more than 50% probability, it should be something around half rate. We think it should be something around 180 or something, but which is not. It's around something like very small. It's n equal to 23. Yeah. Is everyone with me? Till now it's clear. We hate waiting. There are 16 people went to OAT. Out of them, 8 are girls who are having 50 rupees each with them, and 8 are boys with 100 rupees with them. The entry ticket is also rupees 50, and the counter started with no money. If the people are going randomly, what is the probability that none of them waits for change? Okay, for this to happen, first tell me how should the people go to the ticket counter? What are the favorable cases? Like how the people should be arranged while going to ticket counter? Starting has to be a girl, two girls, then one guy, alternate girl and boy, alternate girl, boy, one is case. For each boy, a girl must go before him. The number of girls before a boy should be greater than or equal to number of boys until then. Yeah, it's actually correct. All the other things will be subcases of that thing. The number of girls before a boy should be greater than or equal to number of boys until then. So that the ticket counter will have some change to give whoever boys come, whoever comes next. Yeah, yeah. All okay. So, what are the favorable arrangements of the persons? How many total arrangements are possible? So, the favorable cases are those should be more number of girls than the boys in front of any boy. Persons don't wait. So, how many such possible cases? This is given by the Catalan number. Catalan number. You can refer to the YouTube link we have given below, and if you have any doubts in that, we can discuss in the group. You can explore Catalan number. It's a very nice thing. You have different concepts build up upon that single Catalan number. You can try reading them. You'll enjoy it really. So the Catalan number is given by 2n cn upon n plus 1. So here n is equal to 8 girls or 8 boys. So n is equal to 8. So the number of possible arrangements that the people can stand in queue for favorable cases is 16c8 by 9. So what are the total number of possible standings in a queue? Which is 16 factorial. Number of arrangements of 16 people. So hence the required probability is favorable cases upon the total cases, which is 16 choose 8 by 9 into 16 factorial. Is this good? Are you with me? Yes? Yeah. Conditional probability. Conditional probability provides us with a way to reason about the outcome of an experiment based on partial information. So what does this mean? So let's again go back to our tossing problem. So you are tossing a coin twice and you are said that the first toss is a head and you are asked what is the probability to get both heads. So this is what, like, you are provided partial information regarding the first toss and you are asked information regarding the complete, like 2 tosses. Yeah, I can see different answers. You can try this question. Like you are tossing a coin twice, and you are get given that the first toss is a head. What is the probability that you get both tosses head? There are different answers: 0.5, 0.25, 0.5. Yes. So you are performing a event of tossing a coin twice, and you are given that the first toss is a head. What is the probability that you have both tosses to be head? Yeah, we'll see it through some examples. Hmm. In an experiment involving two successive rolls of a die, you are told that the sum of two rolls is 9. How likely is that the first roll was a 6? Or in a word guessing game, the first letter of a word is T. What is the likelihood that the second letter is an H? So, in these examples, you can see there is some information regarding the experiment, and you are asked to calculate the probability. That is, you are putting some conditions on the outcomes and you are calculating the probability. So, this is what conditional probability is. Yeah, is it clear till now? Yes. Conditional probability. More formally, in a given experiment corresponding to a sample space and a probability law, suppose that we know that the outcome is within some given event B. We wish to quantify the likelihood that the outcome also belongs to some other given event here. We want to find the conditional probability of A given B, denoted by P of A given B. So, what does this entire
Guys, please wait for 2 minutes. Uh, I think there's a small connection issue. Guys, we'll be taking the attendance right now. So I'll share you a QR code for the attendance. So you just have to scan the QR code. Uh, I'll be sharing that. Give me a minute. Are you able to see the QR code? So we'll be taking attendance for session using the QR code. So please scan the QR code, and yeah, I'll put the link also in the chat box. So you just have to scan the QR code. You have to enter your name and email address, and you have to submit. So I hope that's fine. We'll wait for 2 minutes till everyone else has filled it.
Oh, am I audible?
Yeah, you're audible. I think should be fine.
Someone can confirm. Sorry for the inconvenience. Some small network issue. Okay, we'll start again. Sure. So, yeah. So more formally, given an experiment corresponding to a sample space and a probability law, suppose that we know the outcome is within some given event B. We wish to quantify the likelihood that the outcome also belongs to some other given event A. We want to find the conditional probability of A given B denoted by P of A slash B. So what does this mean? So in the previous example, we saw like tossing a coin twice. If the first toss is a head, then what is the probability that both the outcomes are heads? So how can we relate that thing to this statement? So what do you think is the event B in that example? So B is the event of getting head in the first toss. And what is the event A? So getting both heads is our event A. So we want to calculate the conditional probability A given B. That is getting both heads given the first toss is a head, which is denoted by P of A given B. The expression for conditional probability is given by P of A given B is number of elements in A intersection B upon number of elements in B. So how do you relate this to the example? So what are the number of elements in A intersection B? So first, what is the set B? So B is HH or HT. What is A? HH. So number of elements in A intersection B. It is HH, like one element. Number of elements in B. HH and HT, two. So what is the conditional probability of A given B? It is half. You can try verifying the conditional whether the conditional probability satisfies the probability law, non-negativity, additivity, and normality. Properties of conditional probability. The conditional probability of an event A given an event B with P of B greater than 0 is defined by P of A intersection B upon P of B. Conditional probabilities can be viewed as a probability law on a new universe B because all of the conditional probability is concentrated on B. In the case where possible outcomes are finitely many and are equally likely, we have P of A given B is number of elements of A intersection B upon number of elements of B. Is that clear? So what this basically means, before we have a sample space S, the complete universe, what is probability of A, P of A, which is nothing but what is the chance of occurrence of A in the entire all possibilities of S. But when we are saying that probability of A given B, like we are sure that a event B has occurred in the sample space. Then we want to calculate what is the probability of A occurring given that event B has already occurred. So it is the things which are common to A and B, because B should definitely occur. So all everything can A and can't occur, because some of them might not happen when B have already occurred. So we are taking what are the elements that are common to both A and B, and we are sure that the elements are from only B, like as B has already occurred. So the conditional probability is given by P of A given B as P of A intersection B, that is in both A and B, and we are sure that they are from P of B. So now our new sample space is concentrated to P of B. So the conditional probabilities can be viewed as a probability law on a new universe B, because all of the conditional probability is concentrated on B. In the case where all possible outcomes are finitely many and equally likely, we have P of A given B as number of elements of A intersection B upon number of elements of B. Hope it's clear. Multiplication rule. We assume that all the conditioning events have positive probability. We have P of A1 intersection A2 intersection and so on intersection AN is equal to P of A1 times P of A2 given A1 times P of A3 given A1 and A2 and so on P of AN given A1, A2 and so on AN minus 1. So you can verify the multiplication rule by repeatedly applying the conditional probability definition. So in the first step, you can take A2 intersection A3 intersection and so on AN as your probability, like as your B, and you want to take P of A intersection B as P of B times P of A given B. So which is P of A1 times P of A2 given A1 and so on, that complete thing. And you can repeatedly do this and you can get this formula. Problem. Like, see. To understand this clearly, we'll see an example. 3 cards are drawn from an ordinary 52 card deck without replacement. What is the probability that none of the cards is a heart? So someone can answer. 13C3 upon 52C3, 13 head cards in a deck. So mm, I have asked that none of the cards is a head. So we'll see. Let's apply multiplication. let us define the event AI as the event of not getting heart on eighth card. So then the required probability is P of A equal to P of A1 intersection A2 intersection A3. That is, you should not get a heart in the first card, you should not get a heart on the second card, you should not get a heart on the third card. So now applying multiplication rule, we get P of A equal to P of A1 and P of A2 given A1 and P of A3 given A1 and A2. So why are we doing this? What we need is we should have none of our cards to be containing a heart. So the first card should not have a heart. So which is P of A1. And we have when we draw the second card, we want both the cards to be not a heart. So the first card should not be a heart and the second card should not be a heart. So it should be the second card is not a heart given that the first card is not a heart, which is P of A2 given A1. Similarly, for the third card. Therefore, probability is given by like 39 non-heart cards will be there upon 52 total cards. And then when you draw a card which is not a heart, the number of cards which are not having a heart will be 38 and total number cards are 51. So the second thing will be 38 upon 51, which is P of A2 given A1. And then if you pick the second card which is also not a heart, the total number of non-heart cards is 37 and total number of cards are 50. So P of A is 37 upon 50. Is that clear? Yeah, you can do use 39 C3 upon 52 C3. No, it's correct. So basically when you simplify it, you and write each term, like you can split it into terms, you'll get the same thing. So total probability theorem. Let A1, A2 and so on AN be disjoint events. Form a partition of the sample space and assume that P of AI greater than 0 for all I equal to 1 to n. Then for any event B, we have P of B equals to sigma I equal to 1 to n, P of A1 intersection AI intersection B, which is equals to sigma I equal to 1 to n, P of AI times P of B given AI. So what is this? So if this is our entire sample space, we are dividing it into different parts, which are disjoint events like this is A1, A2 and so on something. When we want to get the probability of B in the sample space, so B is somewhere located in the sample space. So uh, what P of B is same as P of S intersection B. Because sample space like the universal set intersection something is same as intersection like the same set. So P of we can write P of B as P of S intersection B and S we can write as A1 union A2 union and so on AN. Then when you split up it into each term, we'll get P of AI intersection B summation I equal to 1 to n. So by applying the conditional probability formula, we get sigma I equal to 1 to n P of AI times P of B given AI. Is that clear? Is that clear? Everyone with me? So you can try this problem for 2 minutes. You enter a class of you enter a chess tournament where you have a probability of winning a game is 0.3 against half of the players. Let's say type 1 and zero point 0.4 against a quarter of players. Let's say type 2 and zero point 0.5 against the remaining quarter of players. What is the probability that you win a game? Mm, yeah, 0.375, 0.325, yes. So we'll see. Let's apply total probability. Let AI be the event that you play with player of type I. This is a partition as you have to play with a player, he must be of some type. Like you choose any player, he should be either player of type 1 or type 2 or type 3. So AI is a partition. So so what is the probability of your winning? Like you can win by playing with player of type 1 and you can win. Or you can play player of type 2 and you can win. Or you can play player of type 3 and you can win. So this term P of A1 denotes that probability that you are going to play with player of type 1 who is half of the total, so which is zero point 0.5. So when you play with player of type 1 you can win with probability of 0.3. So the probability of winning when you play with player of type 1 is zero point 0.5 times zero point 0.3. Similarly, the probability you play with player of type 2 is 0.25. When you play with player of type 2, you win with a probability of 0.4. So the probability that you win while playing against player 2 is 0.25 times zero point 0.4. Similarly for the third one. So the total probability that you win. So the total probability will be sum of three probabilities that you play with either with type 1 or type 2 or type 3. Is that clear? So yes, one more example. Prob. We rolled a four-faced die. If the result is either 1 or 2, we'll roll once more, but otherwise we will stop. What is the probability that the sum total of our rolls is at least 4? See, to clarify, you can roll at most twice. If you get in the first roll, if you get 3 or 4, you will stop. If you get either 1 or 2, you will get only one more chance. You can try this out. So is the question clear? Could see different answers. Yes. So we'll see. Let AI be the event that the die shows one eye on the first roll, and B be the event that the sum of rolls is at least 4. So what we want is P of B. What we want ultimately is P of B. So we'll see. So P of B is nothing but by total probability theorem, sigma P of AI intersection B. So we need to know if we get 1 in the first row, what is the probability that we will get at least 4? If we get 2 in the first row, what is the probability that we will get at least 4? And so on. So yeah, when you get 1 in the first row, you will get one more chance. So you have 4 possibilities for the second throw. So for you should get at least 4, you should throw either a 3 or a 4. So the probability P of B given A1 is 2 upon 4, which is half. When you get a 2 on the first throw, you will get one more chance and you can get 2 or 3 or 4, so that your sum of both the rolls exceeds is at least 4, which is 3 upon 4. If you get a 3, you will stop, so you can't reach 4. So P of B given A3 is 0. Similarly, P of B given A4. If you get a 4, you are done and you don't have one more throw. So P of B given A4 is 1. So applying total probability theorem. Since all of P of AI equal to 1 by 4, we can write it as sigma I equal to 1 to 4, 1 by 4 times P of P given AI, which is 1 by 4 times 1 by 2 plus 3 by 4 plus 0 plus 1, which is 9 upon 16. Yeah, I could see many of you give 9 upon 16. Yeah, it's correct. So let's, okay, for few of them who missed attendance, we'll take the attendance right now. Others can put your comments like regarding what you know regarding Bayes theorem and all. Let me know. Am I audible now? So you can scan this. We'll take attendance for 2 more minutes and then we will continue. Hope those who missed attendance gave the attendance. So moving on further, Bayes theorem. So let A1, A2, and so on, A and B disjoint events that form a partition of the sample space. Assume that P of AI greater than 0 for all I equal to 1, 2, and so on n. Then for any event B, such that P of B greater than 0, we have P of AI given B is equal to P of AI times P of B given AI upon P of B. So don't get scared by too many symbols or something. It's very simple. So uh, what Bayes theorem says is, like, our sample space is partitioned into many different parts like A1, A2, and so on an. And you are said that event B has occurred. So what is the probability that a certain event AI has occurred and then B has occurred? So P of AI intersection B is given by P of AI into P of B given AI. And P of B we can calculate from total probability theorem. The same expression we have put in the denominator. So let A1, A2, and so on. It is used to get the probability of particular factor causing the event. So it's like there can be many factors causing the event, and we want to know the effect of a particular factor on that event. In such cases, we'll use Bayes theorem. So, for example, you can go to college by walk, by bicycle, with probabilities P and Q, like on time, with probabilities P and Q. It is given that you have reached on time, like you went to college on time. What is the probability that you went by walk, or what is the probability that you went by bicycle? All such situations will be taken care uh, by using Bayes theorem. Yeah, is that fine? Clear till now? So someone can respond. Is that fine? Like you got idea what Bayes theorem is and what kind of things Bayes theorem is going to take. Yes? Yeah. So let's apply Bayes theorem. So we'll take the same previous problem, but in a different version. You enter a chess tournament where you have a probability of winning a game zero point 0.3 against half of the players of type 1, zero point 0.4 against a quarter players of type 2, and zero point 0.5 against the remaining quarter of players. There previously we have calculated what is the probability that you win. Now they are saying that you already won. What is the probability that you played against players of type 1? So you can try it for 2 minutes. Is the question clear? So 0.4, 2 upon 5. Yes, we'll see. Let A be the event that you play against type I players. So as before, it's a partition, and B be the event that you win a game. So what is the probability that we are asking in this question? It is given that you won a game. So it is given B. And what do you want? You played against players of type 1. So we want probability of A1 given B, which is equals to the numerator is you play with player of type 1 and you win. That is P of A1 times P of B given A1. So you are playing with type A1 and you are winning. So which is P of B given A1. And the denominator is the total probability that you are going to win, which is 0. Which is equal to 0.5 into 0.3 upon 0.375. That 375 is coming from the previous calculation which we did for total probability for the same question. So which is 0.15 upon 0.375. So which is apparently equal to 2 by 5 or 0.4. So we'll see one more example. So this is the same question from previous one. So you can try this out. We roll a 4-faced die. If the result is 1 or 2, we roll once more, but otherwise we stop. Given that the sum total of rolls is at least 4, then what is the probability that the die rolled is at least that the die is rolled at least twice? So first let me know, when will you roll the die twice? Yeah, you can see answers 5 upon 9. So first answer, like when will you roll the die at least twice? You get either 1 or 2. Yes. So let A be the event that the die shows I on the first roll, and B be the event that the sum of rolls is at least 4. To roll the dice twice, it should show either 1 or 2 on the first roll. So what is the probability we want? We are given the event B and we want either 1 or 2 to happen. So the required probability is P of A1 union A2 given B. So by the addition property, additivity, we can split it like P of A1 given B and P of A2 given B. So these are all the probabilities which you saw from the previous one, and we are calculating the total probability P of B, which is 9 by 16. So now we are applying Bayes theorem. What is the required probability? That is 1 by 4 in the numerator, the first term in the numerator, 1 by 4 into 1 by 2. That is, you get 1 in the first row, and the probability you get some at least 4 when you get 1 in the first row, which is P of B given A1, which is half. So 1 by 4 into 1 by 2. Similarly, the second term indicates when you get a 2 in the first row, which is 1 by 4 times 3 by 4. So the required probability is 5 by 9. Is this clear? Hope this is clear. Yes. What is the intuition behind Bayes theorem? Like many would have questions like when to apply Bayes theorem. When you are given a problem in which you can reach destination through different possible paths, and you are given that you are already at the destination, what is the chance that you chose a particular path to reach the destination? So when such situations you see in the question, then you should apply Bayes theorem. So what are we doing basically? To be precise, what does the denominator and the numerator indicate? The numerator indicates the probability that you reach the destination, that you take a particular path. Like you can go from city A to city B through either path 1, path 2, or path 3, let's say. So the numerator indicates that you chose path 1. What is the probability that you are going to the city B? And the denominator indicates the total probability that you reach the destination along all possible paths. So denominator gives the total probability that you reach to city B, whatever the path you have chosen. Example, Arav is at Mandakini. He decided to go to OAT. He can either go by walk or by bus or bicycle, not being late with probabilities A, B, C. Given that he is at OAT on time, what is the probability that he came by walk? So in this example, our destination is to reach OAT by time, on time. So what are our paths? He can go either by walk or by bus or by bicycle. What is the probability we are asking? Given that he reached OAT on time. So we are asking what is the probability that he came by walk? When you see some similar problems, remind that you have to apply Bayes theorem. Is that clear? Everyone with me, is that clear? Hope this is clear. Yes. So I missed something important. I receive only two kinds of mails, either important or spam. It is estimated that half of the emails are spam. My friends Kailash and Atreya developed a software that filters the mails before they reach my inbox. They claim that their software can detect 99% of spam emails, and the probability that it marks important as spam is 5%. Now, when email is detected as a spam, what is the probability that I missed a important email? That is, they put me in trouble. Yeah. You can try this question and we'll provide the solution for you in the slides. So when such situations you can see, you can think of applying Bayes theorem. So let S, I be the events that the incoming mail is spam and important, respectively. And let A be the event that a mail is identified as spam. So P of S, given that half of my mails are spam, so 0.5. P of I, so the remaining 0.5. P of A given S. So if a mail is spam, the software identifies it with probability 0.99. So it's P of A given S. If it is important, then it is identified as spam with probability 0.05. So P of A given I is 0.05. So now what we want? We want to calculate the probability given a mail is identified as spam. What is the probability that it is a important mail? So I want given it is identified as a spam. So given A, I want to know what is the probability that it is important. So I want to know I given A, P of I given A. So applying Bayes theorem, which is P of I times, so it is important and it is identified as a spam, upon what are the possible outcomes that it is identified as spam. So you can plug in the values and check, it comes out to be 0.048. Yes. Are you under attack? Radar detection. It's also one more application based on Bayes theorem. You can try this out. Later we'll provide the slides. So you can take a screenshot and try this. So basically, if you are clear with Bayes theorem, you will get a clear idea on total probability theorem. So yeah, moving further, independence. We define conditional probability P of A given B to capture the partial information that B provides about A. An interesting case arises when B doesn't provide any information regarding A and doesn't alter the probability of occurrence of A. That is, P of A given B is simply P of A. So, what does this mean? So, you are tossing a coin twice, and it is given that your first toss is a head. What is the probability that your second toss is a tail? It is half, simply half. So, the fact that the first toss is a head doesn't affect the probability of the second toss being a tail. So, such situations are considered as independent events. So, when the above equality holds, we say that A is independent of B. Note that by definition, P of A given B is P of A intersection B upon P of B, which implies P of A intersection B is equal to P of A times P of B. Observe that this definition can be used even when P of B is 0. Since the expression P of A intersection B is P of A into P of B is symmetric. So if A is independent of B, then B is also independent of A. So we can say that A and B are independent events without any ambiguity. Like we have no need to think of whether A is independent of B and B is not independent of A like that. So we can with ambiguous we can unambiguously say that A and B are independent events. So consider an event experiment of two successive rolls of a four-sided die with all 16 possibilities. All outcomes are equally likely with a probability of 1 by 16. Check whether the given events are independent or not. So you can check this after the session. Like you make sure that you check whether these are independent or not. So conditional independence. Here we are going to discuss about the independence of various events with respect to conditional law. In particular, given an event C, the events A and B are called conditionally independent if the following equation holds. That is, P of A intersection B given C is P of A given C and P of B given C. What we are doing? It is nothing but like we are doing the same thing. Previously, we didn't have the condition C. We have P of A intersection B is P of A and P of into times P of B. So similarly, we are defining it by putting a condition of C. So putting a condition is nothing but concentrating our sample space. So by applying conditional probability and the multiplication rule, it's P of A given B intersection C equals to P of C. So from the above equation, you try deriving this equation. So it is same as whether B happened or not, it is not going to alter the probability of A occurring given C. In other words, additional occurrence of B when C has occurred doesn't change the probability of occurrence of A. So consider two independent fair coin tosses in which all four possible outcomes are equally likely. H1 first toss is a head, H2 second toss is a head D. The tosses have different results. Check whether H1 and H2 are unconditionally independent or not, and also check whether they are conditionally independent or not with D. So you can try calculating the required values to check the independence and verify whether they satisfy the condition or not. So once after the session, you make sure that you check whether they are conditionally independent or not, whether they are unconditionally independent or not, and you can try different possibilities as well. So moving on. So till now we have seen the basics of probability and different important theorems of probability and rules how to calculate probability of different events. Now we are entering random variables. What is a random variable? It is a real valued function of the outcome of the experiment. So like if you are tossing a coin 3 times, you can choose number of times the head occurred as a random variable. So the number of times head occurs is a random variable. Random variable associates a particular number with each outcome called as numerical or experimental value. So if you get HH, 2 associates to HH. If you get HT or TH, you get 1 associated with them. If you get both tails, you get 0 associated to them because we are taking the random variable as number of heads. For example, let's take the event of tossing a coin. We can take number of heads or number of tails as the random variable. Hope this is clear. And types of random variables. Similar to discrete and continuous probabilistic models, we have similar random variables. A range is finite or countably infinite. So you can count number of heads or number of tails. Such things are such things comes under discrete random variables. Continuous random variables. A range is uncountably infinite. So choosing a particular number from a number line. So that number can be anything. Like from 0 to 1, you have 0 0.1, 0 0.011, and so on. So the range is uncountably infinite. Such things comes under continuous random variable. Has a probability mass function that gives probability of each value. So since you have finitely number of values, you can associate like the weight for that particular random variable to occur. So when you toss a die, let's say x is the random variable associated with the number showing on the top face. So you can associate PMF for x equal to 1, x equal to 2, x equal to 3, and so on, x equal to 6. Whereas a continuous probability function, since similar to the probabilistic model, you can't associate a probability to a single element. So you have to take an interval. So we have a probability density function that the random variable takes a value from v to v plus dv over the interval. Calculating PMF. PMF is defined as P capital X of small x. So that is the probability that the random variable is equal to small x, where capital X is the random variable and small x belongs to range of capital X. So collecting all possible outcomes that give rise to the event capital X equal to x and add their probabilities to obtain P capital X equal to x. Since we take the PMF over the entire range, it covers all cases. That is sigma x P capital X of small x equal to 1. So what does this mean? When you throw a dice, you can get either number 1, 2, 3, and so on 6 on the top face. So what is the problem? So let us denote x is the random variable associated with the number on the top face. So what is P capital X of 1? Can someone respond in the chat? So I'll repeat the question. When you throw a dice, if you are associating a random variable to the number appearing on the top face, what is the probability that the number is 1 on the top face? Yeah, 1 by 6, which is nothing but we're saying the probability, like we're simply representing, we're associating a random variable x to the number on the top face. So what is P capital X of 1 mean? The probability that small x equals that capital X equal to 1. That the probability of getting 1 on the top face, which is 1 by 6. So what is the second expression mean? Sigma x, sigma of x, px of x. So getting any number on the top face, which is probability 1. So it includes all the cases. So for example, let the experiment consisting of two independent tosses of a fair coin and let x be the number of hits obtained. Then probability mass function of capital X is given by. So you can see P of x equals to 0 or x equal to 2. X equal to 0 means getting no head. So what are the possibilities? Getting both tails. So t comma t. What are the total possible outcomes? H, uh, HH, HT, TH or TT. So total 4. The probability of getting either 0 heads or 2 heads is 1 upon 4. And when x equal to 1, getting 1 head, which is HT or TH. So we have two possibilities. And total number of possible outcomes are 4. So the probability of x equal to 1 is 1 upon 2. Otherwise 0. So you can't get more than 2 heads or less than 0 heads. So otherwise it's 0. So in similar way, you can calculate probability mass function for different random variables and different experiments. So what are the different terms in random variables? Expected value. It is the weighted average of all the values of a random variable and it is denoted by E of x. Variance. It is a measure of spread of your dataset given by expected value of x minus E of x whole square. It is denoted by variance. Variance simply gives you like how much you are spread around the expected value. So expected value and variance. We'll see how to calculate expected value and variance for different kinds of random variables. So for a discrete random variable, expected value is given by sigma x, sigma over all x into x times p of x. So simply in terms, let's say what is the expected value if you are throwing a dice for many number of times? What is the expected value? That is, you take the average of all values over all your throws. What is the expected value of throwing a dice? So it is, you can get 1 with probability 1 by 6, 2 with probability 1 by 6, and so on, 6 with probability 1 by 6. So the expected value will be 1 by 6 times 1 plus 2 plus and so on 6. Yeah, it's 3.5. So this is how you calculate a expected value for a discrete system. For a continuous system, it is nothing but, since it's continuous, it's nothing but taking from over the range of entire values of x from minus infinity to infinity, x times fx of x dx. So similarly, what is the variance? Like, see, now you treat capital Y equals to x minus e capital X of x whole square as your new random variable. Then variance of x is expected value of y. So what you do is similar to the above. So we'll get variance as given formula. And for a continuous probability distribution, again doing the same procedure, you'll get variance of x is given by expected. So what does all this expected value and variance means? Expected value gives the idea of the value of the random variable if you perform the random experiment for a large number of times. So you keep on throwing, like, you keep on throwing the dice. Then if you take the average of all those values over a large number of trials, then what will that average be? It is given by the expected value. Here x is the random variable, like in the above notations, x is the random variable, p capital X of x is the PMF, and fx of x is probability distribution function. Yeah, this is for today. Like, hope you enjoyed the session as much as we enjoyed teaching you all. So, is that clear till now? Whatever we have covered in these sessions.
I wanted to ask one thing. For variance, uh, variance means how much a particular thing varies from the mean, right? So why is there a square term there? Like variance is e of x minus expected value of x, and then we are squaring it. So is there any reasoning behind it?
Like, see, uh, expected value, what happens? Like, your question is, while we are calculating variance, we are squaring it. What happens if you don't square it? That's your question, right?
Yeah, the reasoning behind why we
Yeah.
are squaring.
See, once you try calculating it without a square, you will get to know the reasoning behind. Like, if you do without keeping a square, whole square on it, perfect square without squaring it, you'll get to see the variance comes out to be zero. See,
Okay,
expected
yeah.
value. Yeah, understood.
Yeah,
So
then some will be more, some will be less, and they'll cancel it
yeah,
out.
they will cancel it out.
To
So
keep it in absolute value, we take the square.
we
Fine,
take this.
thank you.
Yeah.
Guys, if you have any other doubts, you can ask in the WhatsApp group also. That should be fine.
And today we will be posting a problem set. So on all the concepts discussed today, so you can try solving them as well. It will give you a nice insights. So if there are any doubts, you can raise your hand. We'll be here to answer you. If no more doubts, we can end the session, and while solving, if you get any doubts, we can discuss in the WhatsApp group as well.
So will we be getting the file which you, the PPT which you showed?
Yeah, you will be getting the slides. We'll post it in the. We'll send the link for it. You can refer them.
Yes, thank you.
Yeah. Hope you all enjoyed this session. If you have really enjoyed, you can react with some good emojis. So if there are no more doubts, we can end this meeting. Yeah, all the best. Hope you enjoyed this session. Anything?
Pradyuman, you can end the meeting, I think. Okay, I should be fine either way. Yeah, okay.
Fine.
Okay then. Hi, we are also leaving. Bye bye.
Bye.